Let's work through some examples of using our net force in the r direction to solve for certain things in these problems. Just start over. Okay, let's work through some examples using centripetal force. So read through this problem, press pause, and then take some time to work through it. At least practice maybe trying to draw your free body diagram, and then press play and we'll go through it together. So one thing you're going to find with these types of problems, we have our new coordinate system r, t, and z, and I want to show the forces in the r direction, the forces in the z direction, and the forces in the t direction. Sometimes there might not be forces in all those different directions, but I still kind of want to look at what's happening in each of those directions. And that's three different directions that we're trying to show on a two-dimensional page, which is very difficult. So the way that I like to do it is I look from two different perspectives and I only consider two directions at a time. So here's what I mean. First, I like to look at what's called a bird's eye view. So from a bird's eye view in this problem, it's going to be like the dad. Here's the dad in the middle. Here's a rope. Here's the inner tube with the kid on it, and he's going to swing kind of in this circle. So from this perspective, I can see the tangential direction and the radial direction. I'm going to also consider a head-on view, where this kid you can consider is being spun, and this kid is like coming out of the page as he swings around. So this would be coming head on towards you, coming out of the page. And so in the bird's eye view, I'm only going to be able to see the tangential direction and the radial direction. The z direction would be coming out of the screen in this perspective. So my axes, I'll have the tangential direction pointing straight down, and the radial direction, the r direction, is pointing to the right, because if the object is right here, that's where those two directions are. And now I can ignore the forces in the z direction. I'm not going to show the forces in the z direction in this picture because it'll be too confusing. I'll show the forces in the z direction in this view. Okay, so right now I'm just looking at, are there any forces in that tangential direction? Are there forces that are always pushing the kid in the direction he's moving or opposite the direction he's moving? Well, if he's going at a constant speed, he's not going to have any forces in that tangential direction. We're going to ignore friction. So there's no forces in the tangential direction. Is there a force in the radial direction? That would be the force that's actually making this object move in the circle, the force that's always pulling towards the center. Like when the kid is right here, the force that pulls this way. When the kid is right here, the force that pulls this way. Yes, there is a force in that direction. There has to be, or else he won't be able to move in a circle. And in this problem, that force is the tension force in the rope. And in this problem, this force is the centripetal force. I don't have to label it extra. I don't have to write the word F centripetal here. I'm just recognizing this force is the centripetal force in this problem. Let's look at a free body diagram for the head-on view. Okay, so from the head-on view, the tangential direction in this perspective is coming out of the page. So I'm not going to draw the tangential direction. I have the z direction, which is perpendicular to the circle. That's going straight up. And then I have the radial direction, which points from my object towards the center. That's going to be going to the right. So the tangential direction is coming out of the page, so I'm not drawing it. And now I'm just going to consider what forces are in the z direction or the r direction. Well, in the positive z direction, I have the normal force. In the negative z direction, I have mg. And in that r direction, I have the tension force. And again, this force is my centripetal force in this problem. Now, if there were friction, I probably would care about what the normal force is, so I'd try to solve for the normal force. But in this problem, there's no friction, so I actually could just look at this and say N equals mg, but I don't even need to do that in this problem. All I want to do is figure out the tangential speed. So the way I'm going to figure out the tangential speed is by looking at my net force in the r direction. So my net force in the r direction is just equal to T. That's the only force, that tension. My net force in the r direction is always, always, always equal to my mass times my acceleration in the r direction. And my acceleration in the r direction is equal to v squared over r, where that v is my tangential speed. So now I can see that this is where I can solve for this value v, and that will be the tangential speed they're asking me for. So I can plug in my tension was 200 newtons, my mass is 25 kilograms, my radius is 3 meters, and that lets me solve for my tangential velocity of 4.9 meters per second. Let's do another example. So read through this one, take some time to think about it. The first thing you might want to consider is which force is the centripetal force in this case. Well, as I said before, if you're not going to be sliding or slipping out of your turn, then static friction is the centripetal force. So we need to know what's the coefficient of static friction. And there it is. Okay, so there's my coefficient of static friction. Let's draw our bird's eye view picture of the car. Looks good. In this picture, the Z direction is coming straight out of the screen, so I'm not going to draw it. And because this car is moving at a maximum, or a constant speed, there's going to be no forces in that tangential direction. If there were forces in the tangential direction, this would be going faster or slower as it was driving. The force that is acting on it from this perspective is this force of static friction that's pointing in that radial direction. So if we look at a head-on view, where my Z direction is going vertical, my R direction is to the right, and my T direction is coming out of the page, so I don't show it. The forces that I have in those directions, well, I have my normal force going up, mg coming down, and then that static friction pushing it to the right. Again, if there were no static friction, this object would not be able to turn. It would not be able to make a circle. So let's look at my net force in the Z direction. My net force in the Z direction is, well, I have N in the positive Z direction and mg in the negative Z direction, so I have N minus mg. And my net force in the Z direction is always, always, always equal to my mass times my acceleration in the Z direction. This object is not going to accelerate in that Z direction, so that acceleration there is 0, which means my net force in the Z direction is 0, which means N minus mg is 0, or N is equal to mg. Now, that might have been obvious to you from the start, which is fine. You don't have to go through all these steps if it's obvious to you that this object will not be accelerating in the Z direction, and there are no other forces in that Z direction besides N and mg, and we're not on an incline, then you can jump straight to saying that N is equal to mg. But if you're not sure about it, here I've done it all for you. Let's come back to, well, actually we can get it from either perspective. We can see what's the net force in our R direction. In our R direction, we have static friction. I want to know the maximum speed we can go. So that means I want to know what's the maximum force that static friction could ever supply. So my net force in the R direction is just going to be equal to the maximum force that static friction could ever supply. My net force in the R direction is always, always, always equal to my mass times my acceleration in the R direction. And my acceleration in the R direction is always equal to v squared over r. So in the end, I can say my force of static friction is equal to mv squared over r. That maximum force of static friction is equal to mu sub s times my normal. And in this case, my normal is equal to mg, so I put that in here. So now what I've done down here is I plugged in, instead of the maximum force of static friction, I plugged in mu sub s times mg. And I've set that equal to mv squared over r. And this is going to get me that maximum speed. The m cancels, so the mass doesn't even matter. And now I can just plug in the values I know for my coefficient of static friction is 1, g is 9.8, and the circle that we're making has a radius of 50 meters, so I can find the maximum speed is 22 meters per second.